Hello, my name's Jeff Rowe. This is a presentation that I gave at the Southeast Asphalt User Producer Group on November 14th, 2023. And this is a second recording of this that I thought I would make and make available to everyone. So what we have in our industry at the moment is something that I've called a jungle of different parameters, and sometimes we don't see the wood for the trees. There's so many different parameters being proposed, and this talk is going to focus on some linear viscoelastic parameters. And while this is looking at those parameters in the linear region, we should note that we do recognize that nonlinear parameters are also needed, but really that's a separate discussion. So for now, we're going to talk about the parameters in the linear viscoelastic region and see what we can do. So our industry choice. At the moment, we have several parameters that are being proposed. The R value from the Christensen-Anderson model, the delta TC from bending beam rheometer, the phase angle is in the specifications based on work that Pavel Chris did, and some folks have looked at the crossover modulus previously. The question that I have is, do we need all four parameters, or can we just adopt one? All of those parameters define the shape in the high stiffness region of the master curve. The other things that we have to be careful about is some of those parameters are not independent, but are dependent on others. For example, the R value is dependent upon an estimation of the Glassy modulus and the crossover modulus. Some of these parameters can be dependent when they're extrapolated or calculated using a model fit. So the question that I have is, are we better using parameters that lack dependency and we can measure? And what about that point versus shape parameter? I'm going to put a thought at the end of this presentation on the Glover-Rowe parameter and how that we might calculate that and how that's used. So what are we trying to do with linear viscoelastic parameters? We've seen these master curves that folks have, and what we're showing here is two representations of the sharp data for the original, what we call the 8 core asphalts, and the 8 core asphalts were the work that all the sharp researchers in the late 1980s, early 1990s were encouraged to do their work on, as well as other asphalts as well. The left-hand representation is the complex modulus, or G star, shown against frequency at a reference temperature of 25 degrees. And the right-hand side is a plot of G star versus the phase angle, which is commonly referenced as the black space plot. And you can see there are different shapes. This one here, you have to have a reference temperature. As I said, this is 25. This one is really independent of reference temperature. And the different curvature for the different binders here really represents the degree of structure in those asphalt systems or asphalt binder systems. The flatter ones might have more asphaltenes typically. So the flatter ones I would describe here as the, say for example, this AAM, this binder here, which is AAG, is California Valley binder, and is maybe more typical of what in the old way of things we would call a sol binder, low asphaltene content product. Now, if we look at the stiffness of the material and we think about how the material fractures, we can take a plot that looks like this. This is data from a direct tension test, and what we've done here is taken the energy as being the area under the stress strain curve, and we've plotted that area under the stress strain curve against the relaxation modulus that represents the time of failure. So in this case here, we can see that the energy starts off very low at lower values of stiffness, and at higher values of stiffness again it drops down low, but it goes through a peak in between. And over at this side of the plot we've got more brittle behavior, and at this side of the plot we've got more behavior associated with ductile or flow type behavior. In fatigue, Dave Anderson has called this instability flow, and this as true fatigue. And we go through this transition where we have a peak somewhere around about 10 to 30 megapascals, maybe 10 to 50 megapascals, I've said here in the slide, in terms of where this transition occurs. But interestingly, if you see the fracture type behavior, everything's occurring between about a megapascal and 1e to the 9 pascals, so 1000 megapascals. Something's occurring in that region. We don't have anything very much going on lower than a megapascal in terms of the stiffness. So now if we look at this graph again, this is the same graph that I showed earlier. What we can do is say, well, this is a megapascal here. That other data was a E of t, so I've just drawn my line a little bit lower to reflect that a G of t is really E of t divided by 3. So what we can say is that cracking really occurs in this upper portion of the master curve. It really occurs in the high stiffness region, and whether you use 1e to the 5 or 1e to the 6 or somewhere in between, what we're trying to look at is the characteristics of this part of the master curve to reflect cracking behavior. Now, what we've done recently is taken a whole lot of binder data and put this into an analysis and try to look at some different parameters. These include modified binders. They include binders with recycled asphalt pavement, RAP, and other recycled materials like recycled asphalt shingles. And there's a large volume of data here. Just to highlight a few things, something like this might be more associated with a recycled asphalt shingle. The binders that curve around here are recycled, sorry, not recycled, but they would be more consistent with polymer modified binders. So very large volume of data, and what I wanted to do was basically analyze this data from both bending beam rheometer data sets and the matching DSR combination data sets, and see what will happen with the parameters that we might be getting. Those 4 parameters: delta TC, the crossover modulus, the phase angle at a constant modulus, and see how these compare when we do the analysis. So if we think about the shape of a master curve and we look at this high stiffness region, this is what we have here. So the Glassy modulus is somewhere up here. Some folks like to fix this at 1e to the 9. My view is that it's not a fixed value. For this particular data set here, which was a PG 6422, this was tested by the Asphalt Institute. We computed a Glassy modulus of 1.18 e to the 9. And if we use that value, we'll have an R value, which is the difference between the crossover modulus and the Glassy modulus of 1.58. If you fix the Glassy modulus, that number becomes 1.51. The crossover modulus here, 3.07 e to the 7, but we should really express that on a log scale. The R value is actually a number, a delta modulus, expressed on a log scale, because it's the log of a Glassy minus the log of a crossover. So we should also express this as a log number. The phase angle at a constant modulus, Pavel Chris in his original work suggested 8.967 as a number we should use. More recently, folks have been using 10 megapascals or even the tan of delta at 10 megapascals. So we come across here, the green is the original number that Pavel suggested. The brown is the 10 megapascals. It doesn't really make very much difference, so might as well go with the 10 megapascals as probably the sensible number. But some of the analysis work I'm going to show you here is based upon the Pavel Chris's work, so it's using that 8.967. But really it makes no difference. So we have a point here we've defined as a crossover modulus. By anchoring this point here also defines the shape of that curve. The delta TC, if you think about it in terms of DSR data, we have a 0 delta TC at about 111 megapascals and a phase angle of about 26.2, I think 26.2, 26.5 degrees C, round about that number. And that's where your 0 delta TC would be. If you're over on this side, you would have positive delta TCs. If you're over on this side, you would have negative delta TCs. But in terms of those four choices, what we're trying to do is describe the shape of the master curve in this region. Now, when we consider this as sort of a specification, we really have a window where we want our binders to lie within. This is a chart that Steph Bradenham presented in TRB in 2020. And really it was in exploring a conceptual approach for specifications to be implemented in South Africa. What we have is an idealized green area where we want paving grade binders to lie between. Binders in this area would be too soft, they wouldn't be practical binders, and this would generally be, they would fail on other aspects. They wouldn't perform in rutting criteria, etc. Binders on this side will be excluded maybe to a delta TC requirement. They'd be too oxidized, they'd be sensitive to cracking. So there's some range in between here that binders are acceptable. And this isn't too different to the approach that NCHRP 959 proposed with an upper and lower limit on a rheological index line. So this blue line here represents a rheological index of 3. This is a rheological index of 1. The numbers proposed by NCHRP 959 are a little different to that, but the concept is not too different. What we've also shown on here is this is the G star divided by sine delta. These are the Glover-Rowe lines that are based upon the original work done by Charles Glover and just converting them to this equation rather than his viscosity function. And then this line here is the fatigue based on G star divided by sine delta, G star multiplied by sine delta being less than or equal to 5,000 kilopascals. So this is what we have here. This point here, where phase angle is 26.2, G star is 111 megapascals, that's where we have delta TC equals 0, where the Glassy modulus is 1e to the 9. So as I said previously, binders in this area here would basically be binders that are controlled by the stiffness, or they would be a delta TC which is positive. Binders on this side would be controlled by the M value, the lower temperature, the lower grading temperature, and they would have negative delta TCs. So let's talk about these parameters, and I'm going to go through these one at a time. First one here is delta TC. Two methods are currently being used in the industry. bending beam rheometer and 4mm DSR. Now, if we look at the data from the DSR, the suggestion is that we should use a different value of stiffness, maybe somewhere around about 142. If we did our interconversion, we would get 111. And really, there's a difference between these procedures being used. And at the moment, I really tend to say that if we're using 4mm work, we should really just consider the delta TC as a forensic tool that we're using from that type of test, and not really using it in a specification sense, because you will get different values compared to what we see in the bending beam rheometer. With regard to the bending beam rheometer, we have to ask ourselves, does the delta TC capture the correct value that we want? And the repeatability of the measurement may be an issue, and we have to ask ourselves also how polymers affect the results. And I like to think what happens when you test a piece of rubber, and this is an eraser. It's got a thermoplastic rubber it's made of, and when you put a load on that, the load will basically, you'll see a load going on and load going off, typically like what you do with a bending beam rheometer. But if you load this material, it won't deform over time. It's basically a viscoelastic solid, and it will just stay like this. So the stiffness curve will look something like this, and the material will have a very negative delta TC, but it won't crack. The butadiene in that material has a TG maybe around about -85, and the material won't crack. And I like to think that maybe this is some of the explanation about why we see these results. These are results that Bob McGuinness presented at TRB in 2022 from polymer modified materials. So the general trend would be, as you take a PG 5828 and you modify it to make a 7028 and a 7628, you would expect to see the performance increase. But the delta TC goes the wrong way. So delta TC doesn't follow the expected performance trend. So there's an issue here in terms of how that material is performing. We'd expect to see an increase in performance where that material doesn't necessarily have an increase in performance. The R value is complicated by the assumption of the Glassy modulus. The Glassy modulus is not always constant, and it would be a lot easier if it was. In this slide here, I've shown some data from Don Christensen's PhD. In his PhD, he presented data analyzed two ways. One using the Christensen-Anderson model, which is the purple data set here, and one using the Dickerson and Witt model, which is the green data set here. Or I should really say it's the same data, it's just been analyzed with different models. And on this axis, I've either shown the beta value from the Dickerson and Witt or the R value from the CA model. They're essentially both values describing the curvature. And then I've shown on this axis the log of the Glassy modulus. And you can see there's a clear trend in terms of the log of the Glassy modulus. The Christensen-Anderson data has a lower trend line, and sort of the average is about 9. Dickerson and Witt has a little bit higher. And I'll explain why this occurs in a minute or two. What we can see is that these values are not constant, And if we remember that R is basically the log of the Glassy modulus minus the log of the crossover modulus, this causes us a problem if we use a constant value for the Glassy modulus. From the bending beam rheometer data, NCHRP 959 suggested that we calculate this using the stiffness at a loading time of 60 seconds from an isothermal stiffness. Now, for the sharp core asphalts, I've done this, and this is the red bars in this graph. And we had, for example, with AAA, 3 isotherms of stiffness, -12, -18, and -24. And you can see, depending on which isotherm you use, we get a different value for the R value. And this is fairly consistent across the whole of the data set. And generally, if I use a higher temperature, so -12 versus -24, I get a higher R value. And that trend is roughly consistent. There's an odd binder here that doesn't quite conform to that, but generally speaking, that trend is consistent. Now, the green bars are basically taking the same data, combining it with the DSR data, and doing the analysis that way. And you can see when you combine it with the DSR data, you get quite a different number. Now, in the case of these green lines, or the green bars here, I've excluded the stiffness below 1e to the 5, consistent with the recommendations that Don Christensen and Dave Anderson made with the use of the Christensen-Anderson model. A little bit more on that limit of 1e to the 5 later on. So you can see that there's a clear difference here that we get. Now, if we consider an R value of 2, then the crossover modulus would be around about 10 megapascals using this assumption here. So the crossover modulus of 10 megapascals, we can compare that to the lowest value we measured in all of this testing of the BBR data. The lowest value we measured in that testing of those sharp core asphalts was 44 megapascals. So this value of crossover modulus, which is being used in the calculation, is really a second extrapolated value because it's 4 times lower than the highest value or the lowest value that we measured. So the R value as computed from this equation, which is proposed in NCHRP 959, relies upon 2 assumptions here. The assumption of the Glassy modulus being 1e to the 9, and the fact that you can extrapolate to a crossover modulus, which is probably about 4 times lower than the stiffness that you are measuring. And this is what causes the variability here. If we look at literature, we really see that there's 3 ways being proposed to calculate the R value. This equation comes from Mike Anderson's AAPT paper in 2011, where he looked at some aged materials. And it's really the same that was published earlier by Sharp and other folks. But you can see that if you take a stiffness at a certain frequency and the phase angle at a certain frequency, and you make an assumption with regard to the Glassy modulus, then you can calculate the R value from a single data point. So you can take one data point and make an estimation of the R value. In a similar way, NCHRP, this is the equation that they proposed, NCHRP 959, proposed that we do the calculation in that way. And that's the data on the previous slide. Those bars at different stiffness values are using that equations. Or we could use curve fitting. We could use the Christensen-Anderson or the modified Christensen-Anderson equation, and we could use curve fitting. And then if you're using curve fitting, you have to be very careful that you exclude this lower stiffness data, You can see how the phase angle fits if you include that lower stiffness data. It's a very poor fit. And you could say exclude it at 1e to the 5, which is this purple line, or exclude it at 1e to the 6, which is this green line here. Personally, I like to use 1e to the 6 as my standard exclusion. I think that gives us a better value. But the value that we have of 1e to the 9 in shear, or 3e to the 9 in bending, that assumption is not correct. All materials are not the same. And this has been well established. To support this, I'll show the work of Dobson. Now, Dobson, in some of his work, showed the effect of different penetration indexes and the results obtained with different penetration indexes versus the G star, and then on this axis he plots 1 with the tan of delta. Okay, so this is 1 plus tan of delta on this axis here. Now the idea is with this really doesn't involve any shifting, but as you project these lines downwards, where they cross this 0 line, gives you an indication of what the Glassy modulus is. Now, if you look here, you've got different penetration indexes going from minus 1.5 to 4.2. So this would be the minus 1.5 and this would be the 4.2. So we would generally say that this might be something which is representing a less oxidation or lower asphaltenes. This might be more oxidation or higher asphaltene content binder. And you can see where these lines intersect are going to be different. And generally speaking, the intersection of these lines, the higher the penetration index, which would be consistent with higher asphaltenes or higher oxidation level, will give a value on this scale where the intersection is higher. So going on from this, let's look at some other data using Dobson's procedure. This is looking at AAM and AAG. The graph might be a little bit easier to read here because the previous graph was from Dobson's original paper. So here I have the 1 plus tan delta, Dobson's how he likes to plot things, versus the log of the G star. So AAM is a very structured binder, and AAG is that California low asphaltene content binder. And you can see the intersection here would be quite different for these two binders. The more structured binder clearly has a higher intersect, and it would suggest that it has a higher Glassy modulus. Going on from that, looking at a PG6422 example. This is the same PG6422 that I showed in the earlier slide, where I looked at where those different parameters are measured. But in this case, I've added in a PAV version of that same binder. And then blowing up this portion of the graph here where we are looking at that intersect, you can see that the PAV version tends to be a slightly higher Glassy modulus compared to the unoxidized or the original version of that binder. So the suggestion here is that as materials age or condition either in the field or in the laboratory, they change. And the conclusion that I make from this is that the Glassy modulus is not constant as defined by our current testing methods and knowledge. Now, going back to literature, you can see various folks have done analysis, and you've got some in the top graph there, some Dickerson and Witt analysis, and some analysis by Mac Carone, and they relate to publications in 87 and 74. And then I've put again the results from Don Christenson's PhD thesis there. And you can see that depending on the assumptions that various folks have made, you get different trend lines. So, the Dickinson and Witt trend line is this. This is another trend line from, a slightly different version of the model. So the question that we have is, well, why are we getting these trend lines? What do they mean? Dickinson and Witt versus Christensen and Anderson, you get a bigger trend line than you get with the Christensen and Anderson model. So what I wanted to do was look at those two types of models and the hyperbola model shape you have with the Dickinson-Witt versus the exponential shape you have in the Christensen-Anderson model. So this is the Dickinson and Witt model, and this shows how it fits to some data. This is where the glassy is down at this end, and this is the viscous or less stiff material at this end. And you can see with their particular model, their form of the model with their beta function that they have in this just results in a kick up at this high stiffness region. The Christensen-Anderson has an asymptote here which sort of levels off. The Dickinson and Witt sort of kicks up. So the conclusion here is that depending on the shape of the model that you have, you will either see larger dependency or lesser dependency in the Glassy modulus versus the model. So Dickinson and Witt, the analysis that we see according to this method always shows a bit more sensitivity on the Glassy modulus compared to the Christensen-Anderson. So to finish with this, I've got a couple more slides to show on some of these calculations of R value and Glassy modulus. This is some data that we tested in April earlier this year. And this is testing was conducted in this case by Ergon or Paragon Technical Services down in Mississippi. And we have original binder, the RTFOT, PAV, and PAV40. And then each of these is fitted to a Christensen-Anderson model. And I've shown some extension of those lines just so you can see how the model fit would extend to the upper part and to the lower part. And this is doing an optimization, a best fit of that data set. And you can clearly see that you get higher stiffnesses with the more aged material at the glassy condition. And if we look at the calculation here, this is showing the R value from those 4 different tests and the estimated glassy. This is the PAV40, this is the PAV20 original and RTFOT and original. Now, where that glassy modulus is assumed to be 3 megapascals, which is the recommendation from 959, we have that R value at 1.41. But it's very clear that the difference in the aging of these materials, or conditioning, it may be a better word to use there, shows that those materials clearly change in terms of their glassy modulus with age. Now, taking this type of analysis and doing this with a larger data set, so this is now doing this analysis with the data set that I showed in one of those earlier slides. This shows how the R value calculated from curve fitting and the glassy modulus vary over a range of conditions. Now, the average here is probably not too far off that value being proposed by 959 workers. But again, clearly it's not consistent, and you're going to get very different results with the assumptions at one level to another. Now, this is the reason you get the different results with those different isotherms. So I showed a graph earlier, and I showed for AAA we had 3 different temperatures for the isotherms, and we get 3 different R values. And that's because you get 3 different points. This would be the high temperature, this would be the next temperature, and this would be the next temperature, those 3 isotherms. If you fit data to that, we can estimate what the Glassy modulus might be. So I have 2 estimations on here. One is from something called the discrete spectra analysis. Some folks call this a Prony series, so that's fitting a Prony series to that data set and estimating where that value would be. The brown dashed line here represents the fit from the Crisis and Anderson model. So I'm reasonably confident that that Glassy modulus is somewhere around about this value that you see with this black line extending here. The purple line represents the NCHRP 959 assumption, and that's clearly different. The crossover modulus is going to be a little bit lower, so the crossover modulus would be somewhere around about here. So depending on the extrapolation, this one would extrapolate just a short bit to the crossover, this one would extrapolate a bit further, this one would extrapolate even further. And we have to remember that the R value is this difference between the crossover modulus and the Glassy modulus. And if you use the model fit, you would use this as the R value. If you use the assumed, you'd use this as the R value. And each of those numbers become different now depending on the assumptions that you have. And this is why the R value as proposed by 959 really doesn't work. Now, recently it's been suggested that let's use the isotherm which is just above the passing temperature. So it's the first passing isotherm. This was a way of looking at trying to reduce that variability from 959 work, and Mike Anderson presented his analysis on this, and he had this black line as his relationship. Now, we know that there's strong relationships between the modulus and the phase angle and the S of t. So this is showing the relationship between the S of the t and the modulus. The blue data is showing the relationship between the M value and the phase angle. So we know these things are interrelated. So the fact that you can say delta TC, which is from bending beam, is related to the R value from either a rheological test or from a bending beam, these things should all be interrelated. Now, if we look at this data, the red data points is the analysis of the sharp core asphalts, which I reanalyzed and produced this blue line, very consistent with Mike's line and about where the NCHRP is proposing their limits. Sort of fits with around about 2.5, somewhere around about 5 on 3 to 5 on this scale, depending on where you take that relationship. So this is gives us a one way of approaching this. But as we are doing this, we're basically taking this stiffness to a value which is closer to a constant stiffness. So as we take this stiffness, say to a constant stiffness, say somewhere around about 150, 200 megapascals, which is where you get that passing grade, basically this equation reduces to being a function of the M value. But the M value is really a measure of the phase angle. So if this is the case, that we're saying that this isotherm corresponding to gray temperature is a preferable approach, then what we're really doing is we're saying as we move the R value to a phase angle, we're getting a better result. So the discussion then becomes, why not just use the phase angle? And this was the approach that Pavel Chris suggested. Pavel suggested in 2020 in his CTAA paper that if we took the delta value at 8.967 megapascals, effectively that describes the shape of the master curve. And I think the industry now is coming to a value of 10 megapascals rather than that original 8.967. This has been implemented in specifications, this phase angle approach, to allow us to use stiffnesses which are higher for the G star times sine delta if the phase angle exceeds a minimum value of 42. So this is an approach that we can use, and let's just see how some of these parameters relate to each other. So looking at the phase angle, I put the phase angle pk there for its Pavel-Chris's number, and that's that number at 8.67. This is a fairly limited data set, but it's just showing you how it relates to R value and how it relates to delta TC. All of these four parameters, the crossover modulus, the R value, the delta TC, and the phase angle at a constant modulus, should all be interrelated, and they are. So this is something we can use. So the fourth choice is we come along and we look at the constant or the modulus value where we have a phase angle at 45 degrees. Some people will call this the crossover modulus. Some people will call this G star vet for viscoelastic transition. So you're transitioning from where the viscous behavior is dominating to where elastic behavior is dominating. And if you look at this data here, you know, this is showing G prime and G double prime, where G prime and G double prime cross, which would basically be here or here, depending on the isotherm you take. That's really a measure of the crossover modulus. So it would be basically this point over here. And in terms of phase angle, we'd have to come in at 45 degrees, and we'd get a crossover modulus again from that number in terms of the modulus versus the phase angle relationship. This bottom graph really shows how we can get a crossover temperature by the assumption of different frequencies. So there's two aspects of this. You get a crossover modulus or a crossover temperature. Crossover temperature is really defining a hardness parameter rather than a shape parameter, but a little bit more about that later on. So we have the four approaches. Now, which one am I most happy with as a parameter? So the delta TC, we know there's issues with that when it comes to modified binders. So I'm not including that further in my discussion here, but rather focusing on the three parameters that we are measuring with the rheometer. If we look at the R value versus Pavel-Chris's phase angle, we can see that we have this amount of scatter. If we look at Pavel-Chris's phase angle versus the log of the crossover modulus, we can see we have a much reduced scatter. Remember, all these methods should be correlated to each other with a high degree of correlation. The fact that the R value loses the correlation is really because of the different assumptions going into that method, and the fact that we always have to extrapolate the data sets. We never have a measure down at 1e to the 9. So we're always doing a certain amount of extrapolation. And when you're fitting a curve, it's very sensitive to any minor deviations or shape in that curve. So since we can measure the phase angle quite easily at a constant modulus, and we can measure the crossover modulus, these are both values that we measure. They're within our measurement region. There's a high degree of correlation there. One of the questions that we asked ourselves was, what about this cutoff? And we, in the original work where von Christensen and Dave Anderson, the suggested cutoff was 1e to the 5. But since the early 90s, we've been using a lot more polymer modified binders, and we get this type of curvature. And I'll show you here, you see this red data, how it curves around like so here. And the point where that sort of curves around, where we can avoid including that in the calculation, is really about 1e to the 6. And that's consistent with where fracture occurs. So remember, the fracture is all occurring at 1e to the 6 and higher. So we don't really need to include the data below 1e to the 6 in our calculations if we are just looking at fracture considerations. So the improvement we get here is going from an R squared of 0.97 to an R squared of about, well, 0.99 in this case, in terms of the data set. If you look at the R value, we've gone from 0.83 to 0.91. So that's looking at the intercorrelation between Pavel-Chris's phase angle and those two numbers. So based on this, I'm considering that it's better to use a cutoff at 1e to the 6 rather than 1e to the 5. It deals with the polymer modified binders in a better way. Then what I've done is try to look at some other data sets. So this is a data set produced by NCHRP 959. They didn't analyze it in this manner, so I decided I would take their frequency sweep data and plot the data, the phase angle at a constant modulus versus the crossover modulus, and compare it to the data set that we have. And you can see that two data sets lie virtually on top of each other. So this is a good confirmation. And even the fact that the data set produced by 959 does have a little bit of feathering in terms of discontinuities here. Maybe I'd like this data to be a little bit cleaner and to go a little bit further. We still end up with an R squared of 0.96. So it's still a very good relationship. So these are the only two of the four parameters that can be obtained by direct measurement. And when you can measure things directly, that's a huge advantage. So this is an example of, you know, how we might be having a scheme to measure some of these parameters. This is a binder certificate. Again, this is one that was developed by Paragon Testing Services, just of a polymer modified binder. And you always have to report the G star and the phase angle in your results for G star times sine delta. These are actually required report parameters. And that enables you to easily construct a curve of the crossover modulus, say versus the phase angle, or any other. This is a point parameter looking at the temperature of the crossover modulus. And we can, just using interpolation, very easily get these parameters. So if I take the parameters that we're concerned about, like delta Tc, the crossover modulus, the temperature of the crossover modulus, the phase angle at 10 megapascals. In this case, the phase angle at 10 megapascals would require just a minor extrapolation. We'd have to do one more data point down here just to get it. That's 10 megapascals right there. So it would just be a minor extension to maybe the protocols that you're using, and you could use all the existing procedures in ASTM D7175. They'd all be absolutely applicable in terms of the way that we're working. So very easy to measure these parameters. And the thing that I must stress is there's no master curve. There's no complex analysis. We're just treating the interpolation in the same way that we already use interpolation and smoothing with the calculation of the stiffness at 60 seconds and the M value at 60 seconds from the PBR data. In that case, we fit a very simple polynomial and we extract the values. And we could do the same thing here. Very simple to do. So looking at this and looking at the summary for these four shape parameters, we have the phase angle versus the R value versus the crossover modulus versus the delta TC. Our view is that the phase angle is the best method. The log of the crossover modulus is a very close second. But really, we should be as an industry trying to coalesce around one method. And it's interesting that the phase angle concept, either at 27 or 45 degrees, and using this type of approach, was suggested by French workers sometime about 91, 92 time period. So this has already been suggested about 30 years back. Okay, so I just want to make one comment with regard to point parameters. Now, one of the things being considered at the moment is the Glover-Roe to define cracking or aging or how rejuvenators work in materials, etc., etc. Now, NCHRP said that this is a better parameter than G star times sine delta for fatigue cracking, and they're proposing that be used at 10 Hertz. 10 Hertz and 15 degrees C is shown by this blue data point. My question here is well, going to 10 Hertz is 62.8 radians. Why not use 10 radians per second, which is this green point? And basically, you are in this upper part of the curve. You'd have to change the limit marginally for 10 radians to 10 Hertz compared to what they're proposing. But if we look at the original data points, the original data is down here. This is 15 degrees C at 0.005, or at 10 radians and 44.7 degrees C. Those were the original locations developed from Charles Glover's report using time temperature superposition principles. And you can see the 2 points lie on top of each other. If you look at how different models might fit them, this is using a generalized logistic model rather than a Christensen-Anderson model, and all 3 points are basically on top of each other. Then what we can consider is how the test frequency affects these points. As frequency increases from 0.005 to 10 radians, you move to here, and then round to here, and so on. And if you look at different temperatures, you move around this way. So this is 44.7, 25, and 15. So you can play with this curve and where you want to be on this curve by changing the temperature or changing the frequency. My feeling is that 15 degrees C and 10 radians a second gets us in the right place. Remember, cracking's occurring in this region here. The original Glover-Roe numbers are probably just a little bit on the too low side, and this might explain some of the differences we see with polymer modified binders. So in conclusion, the use of the phase angle or logged GC rather than the Rheological index and the delta TC value going to provide us a better tool for specification development, since these parameters have a greater accuracy and precision and within the range that can generally be measured by rheometers. And out of those two parameters, the delta and the crossover modulus, the delta is definitely the better parameter. And, we have to acknowledge Pavel, Chris, and his work in pointing us in that direction. Both of those alternate parameters can be easily measured in the same equipment that we are currently using to define G star times sine delta. So 8mm DSR measurements give us those parameters. We can use the same methods and procedure to determine the Glover-Roe parameter at the same time. And my suggestion is that we use 10 radians per second and we work in that correct stiffness region. And with that, I would like to leave it like that. I hope you've enjoyed listening to this long rambling presentation. If any of you have got any comments or questions and want to reach out to me, please send me an email or text message and I'll try and get back to you. Thank you very much for listening.